let's talk about this issue. Please ask me if there are any comments. Okay. So I will shortly give you an introduction, then I will present some sources of radiation and natural radionuclides in the environment, and finally anthropogenic radionuclides. So, as you know, there are radioactive substances and ionizing radiation everywhere in the environment, even in your body. There is, for example, around 1,000 becquerels of potassium 40, around. So, cosmic radiation is coming to the ground, or cosmogenic radionuclides that are generated at high altitudes of the atmosphere. There may be airborne radionuclides in air, like radon, and you can inhale that. There is external radiation from radionuclides in living nature. Some industrial activities may release radionuclides into the environment, and especially in the soil, there are a lot of natural radionuclides present there. And of course in your body. There may be, for example, radium-226 or potassium-40 in your bones, in the stomach, and different parts of your body. What is the typical external dose rate in India? I don't know. I know that in Finland it is around 0.2, 0.3 microsieverts per hour.
Oh, your radiation level?
Yeah, radiation dose rate level.
Yeah. So it is about we get about.
I think it must be quite close.
Yeah. The
to
annual
that of,
dose is about 2.1 millisievert.
Yeah, annual dose.
Annual dose.
Yeah.
2.1 millisievert in the normal areas, but we have places where we have high doses, like beaches of Kerala, where there is no monazite deposit.
Yeah. Yes.
Where the dose is up to 50 millisievert.
Yeah. All right. And this is also very important. I'm sure that you already know this, but I have to explain this once more. So, radionuclides are transported in the environment as part of the natural cycle of matter, and generally in the same way as stable nuclides. This is more or less general rule, but it's not valid for all radionuclides, but practically most of them. So, you have to understand that ionizing radiation and radionuclides, they behave in the environmental differently. So you have to understand this difference. So radiation is radiation and material is material. And from the perspective of doses to humans, ionizing radiation mostly comes from natural radionuclides in the environment. And this is important thing, because in some specific cases, if you have, for example, cancer and you need some treatment by the aid of not radionuclides, but radiation, then you might have quite big exposures in your body. But normally, the doses comes from environmental radionuclides. So, this is ionizing radiation, and it might happen that radiation from man-made, so-called anthropogenic radionuclides may sometimes have a special role or cosmic radiation, or these human-related activities in hospitals, such as radiation therapy. They may have a special role from the perspective of doses. So, if you have to evaluate radiation exposure caused by the radiation, you have to know characteristics of the radiation and radionuclide location. Is it outside your body or inside your body? So there is external radiation and internal radiation. And if you want to determine activities of the radionuclides, so you have to know characteristics of the radionuclides or the radiation. I have a presentation, I think it's the next presentation on this aspect. Okay, these are the background radiation in the world, in the US or in Japan, and there are also some remarks. I took this from Wikipedia. You can find a lot of information there. For example, this is average annual human exposure to ionizing radiation in millisieverts per year. In the world, total around 3. Karunakara, you mentioned in India 2 point something. 2.1, yeah. In US, it is higher. I don't know why. All right. Karunakara sorry, already said that there are some highly active areas in India too, in this area. And it is because of the monazite sand and thoron inside the sand. It's more than milligray per year, and in some locations even 70 milligray per year. Please look at these publications here. Is it so, Karunakara, that you will send all these presentations to everybody, or?
Yeah.
All right.
Yes.
Nice.
Yeah, we are sending.
Yeah. So, when we are analyze becquerels, not masses, because radionuclides has mass. But why we are talking about becquerels? So the reason is this. So radioactive substances are the most harmful to the living nature when they decay and emit radiation. So the rate of the decay is a better indicator of health effects than the mass. And you can convert the activities here, A, to mass by using this simple equation. So this is molar mass, decay constant, and Avogadro constant. In one of the next presentations, I will show you about LARA application. It is possible to do this more or less automatically. Have you used this LARA application? It's a quite easy application from net. However, in terms of mass, the amount of radionuclides in the environment is often very small. So if we would like to do mass spectrometric analysis from short-lived radionuclides, it's typically not possible. However, it's possible in case of uranium, for example, or thorium, or long-lived radionuclides. So it's easy to detect radiation, quite easy. Let's look at the sources of radiation. I mean, natural radionuclides. So, let's start with cosmic radiation and cosmogenic radionuclides. So, most of the cosmic radiation is particle radiation from the sun and space. For example, solar wind and also galactic radiation, but this solar wind is dominating. Solar wind is a plasma. I mean, nuclides without electrons coming from the sun. And it's mainly protons, low energy protons. There are also electrons, and you know this sun's activity period of 11 years. Now, I think that just now the sun's activity is at the highest. Because I know that especially in the northern part of Finland, but also in the South Pole, there are aurora borealis or aurora australis. However, in solar flares, the energy of the protons may be up to 10 giga electron volts. Galactic cosmic rays, they are coming from the Milky Way, supernovas, black holes, neutron stars, etc., etc. It is more or less constant in time. They are composed of atom nuclides, mainly protons and electrons also, of course, but the particle energies, they are very, very high. Very high. But you can see that if a high energy proton, for example, comes to the higher part of the atmosphere, there is an interaction between molecules of air and following a shower of different radiations. It's a so-called secondary radiation. They are primarily electrons, photons, and muons. Muons are because of the decay of pions. They are located here. I don't know, can you see it? Because this is very small, but the pions are generated there. They are quite short-lived elementary particles. And it is the magnetic field of Earth and atmosphere that protects us against cosmic radiation. Same thing is said here. And I already explained this, that secondary radiation and cosmogenic radionuclides, they are produced in the atmosphere. And these particles must be taken into account when you especially use gamma ray spectrometry. Oh, there is a list of some important cosmogenic radionuclides. I mean important from the perspective of radiation measurements by using gamma spectrometry. Tritium, beryllium, carbon 14, aluminum, etc., etc. There are different nuclides. You can see the half-life here. Main decay mode. They are mostly beta emitters, beta minus emitters, emitting sometimes, for example, in the phosphorus case, quite high energy betas, and also some gammas. Which one of you have analyzed these nuclides in gamma ray spectrometry? Yeah. Yeah. All right. Yeah. So you can see here how carbon 40 is produced. And again, you can have more information from Wikipedia, for example. And you have to note that this list is not complete. And these decay energies are only for the highest intensity lines. Then there are so-called primordial radionuclides, which has been forever in Earth. Sorry?
Electron capture.
Oh, EC, yeah, electron capture. Oh. Yeah. It's a decay mode, one of the decay mode. So it's a little bit difficult to see here. Letters are so small. All right. So Earth was formed, or assumed to be formed, from the solar nebula particles by gravitational collapse. And this nebula contained gas, ice, dust, including primordial radionuclides, like these ones. Note that in this list there is no uranium or thorium. I will explain later this thing. So the point is that because of the long half-life, these primordial radionuclides have survived up to now, up to present day. This is an essential part of or contribution of the Earth's magnetic field and volcanoes, for example, because there is a huge amount of these radionuclides in the Earth core, and they produce heat when they decay. So you can see here some information about the major heat-producing isotopes deep into the core. In this picture, there is a heat flow in terms of terawatts, and this is time here. Let's go to these decay series. I'm sure that you know this series: uranium decay series, thorium decay series, and actinium decay series. I prepared this, let's put it this way. I'm sure that you have seen these kind of decay series in different formats. I put it in this format, showing that most of the radionuclides are, of course, in the soil, in the rocks, in the ground. And there is radon quite close to the surface of. Okay, radon is of course deep into the ground too, but it escapes to air, leading to the fact that these radionuclides are present in air. And there are a lot of radionuclides. When you do analysis, you have to remind that nuclides in the series behave differently. This is very, very essential things. And when you do the analysis in gamma or alpha spectrometry, you have to understand this. We will talk these things later. You can see, or perhaps you can see, let's see. So the letters are so small, okay. You can see uranium series, uranium-238 decay series, nuclides, half-lives, decay modes, alpha energies, beta energies, and gamma ray energies and yields. Let's look at the thorium decay series, same thing here. So this is a primordial nuclide, this one, as uraniums are. This is uranium-235. So this list is not complete. There is a lot of other radiations too. But I selected only the most intensity ones. So, as alpha and gamma spectrometry are the main analysis method, but for example, mass spectrometry, there are different mass spectrometers. They are important for analyzing long-lived radionuclides. And this is, as I told you, this is very, very essential. You have to understand when there is equilibrium or not. Because nuclides in the series may behave differently in the environment. And most of the nuclides in the decay series, they are metals. But there are some important exceptions, like radon, which is a noble gas. Have you used this decay calculator? No, it's quite useful for this natural decay series. I suggest you should use that kind of site, because it's as it was said here, it's a universal decay calculator. But you can also find several decay calculators from the net, which are not so well. Some of them are good, some of them are not good. Have you used this one, or?
I have used
Rad Pro, okay, yeah.
That is good.
Yeah, it's quite simple. Yeah.
Yeah.
But try to use this if you like. Okay, let's look at anthropogenic radionuclides. So, main or most relevant sources are nuclear reactors, I hope that we don't have in the future any nuclear explosions, but there are also radioisotopes produced in industry, hospitals, or research activities. And in case of nuclear reactors, artificial radionuclides can be divided into activation products, which are these one, fission products in the next slide, and transuranics or actinides. What about this cesium-134? It's not a fission product. It's an activation product, in fact. And the reason is that there is a cesium-133 in nuclear fuel, especially when the burn-up is high, and it's generated by the neutron activation of cesium-133. So this is quite common error in understanding what's this cesium. So it's an activation product. So there are a lot of other activation products in the reactors. For example, nitrogen-16 produced by neutron activation of oxygen. Tritium. Which of you are analyzing tritium? Tritium, yeah? You are analyzing, okay. And carbon-14, you are analyzing that, yeah? Generated like this one. So nitrogen-16, it emits high energy gammas, and these two can be analyzed by beta spectrometry. In this course, we are not dealing very much on beta spectrometry because we are concentrated mainly on alpha and gamma. But the methods are more or less same. However, some activation products are generated outside nuclear fuel. I mean, in the tubes, for example, in the primary circuits. These are the activation products. Have you seen these activation products in your studies ever? You have seen? All right. You have? Yeah, all right. Then, about the actinides or transuranics in nuclear reactors. So, these are produced due to the successive neutron captures following alpha or beta decays or other decay types. Perhaps this is the most relevant, and the production looks like this. You have to remember that, for example, in the case of light water reactors, notable part of the fission energy comes from these radionuclides, especially when the fuel burn-up is high. And most of these transuranics, they can be determined by alpha spectrometry, except plutonium-241. It's a beta-emitting nuclide. Yeah. You have analyzed this, I guess so. Have you? Yeah. All right. So this is a list of actinides and radiation characteristics. You have to remember that this list is far from complete. where is plutonium? Okay, you can see this plutonium-241, 14 years. All right. So, main radionuclides in the reactors are, of course, they are fission products. And they are, you know this. Okay, there are different types of reactors. In Finland, we have only light water reactors. And the energy is mainly coming from uranium-235 fission. So how many reactor types are here in Finland? I think, do you have fast breeders here?
Yes.
You have? All right. All right. You know these things. I will not go through any more things.
I think, I think most of the others might not know about the YUM curve.
Sorry, most
might be knowing about YUM curve. This YUM curve, some of the participants might not be knowing about this YUM curve.
All right. So you suggest I will explain more this point.
Just an introduction.
All right. Let's do that. So, as you know, uranium likes neutrons. If a neutron comes together with uranium-235, fission happens, the nuclides disintegrate mainly in 2 parts, sometimes 3 parts. And for example, if it divides into 2 parts, so the mass number might be 100, and the other part is 140 around. And it depends on the how this distribution is generated. Is it question of high energy neutrons or low energy neutrons? Fission comes mainly in light water reactors from thermal neutrons. Unfortunately, just now, I think that I don't have enough time to explain everything in this issue, but you can read this from the net, for example, or books. But the point is that a lot of radionuclides are produced in nuclear reactors. And this is the biggest danger if you want to look at dangers of radiation. So this is why, for example, my organization is just now present in Finland. So we are monitoring, we are watching that reactors are used safely. And there are no releases into the environment. All right, let's go to this part. Okay, I will show one thing, okay? Let's see. So, in the case of fissionable nuclides like this uranium-235, there is more neutrons compared to fission product nuclei, which means that they are mostly beta emitting nuclides because of the neutron excess in the fission product nuclei. I will show you this. You have probably seen this kind of map. So if a heavy nuclide like uranium disintegrates by fission, it happens so that the daughter nuclides, they are in this area or in this area here, and they are going to that way. So first of main part of these nuclides here, in the lower part of this map, they are very rapidly decaying to stable nuclides, which are usually marked as black boxes there. Now, okay, for example, this chain of fission products, it is present here. You can look this afterwards. It's very important to understand this. Okay, I hope that you will later look at these kind of maps. It's very useful in general. Of course, if you are doing your practical job, it's not very often I do not very often look at these maps, but sometimes I have to watch that if I detect some strange radionuclides, I have to check the nuclide map and see what's the origin of that nuclide. All right. So, from the point of view of the fission product release in the environment, especially in nuclear accidents, they are often classified as groups based on their amount of fuel, their chemical form, half-life, volatility, behavior in the environment, or the risk of producing high radiation doses. All right. I cannot go deep into this area because this is a very this is an area which is used, for example, if you want to do risk analysis of nuclear reactors and the consequences that they cause to the people. So you have to understand also these things. All right. There are some important fission products in this slide that might release in a severe nuclear reactor accident. As you can see, they are grouped in different groups. Iodine group. There are some short-lived nuclides. Maybe iodine 131 is the most important. Which one of you have analyzed iodine? You have. Okay. There is cesium group, tellurium group, ruthenium group, lanthanum group, cerium group. And as you see, these groups are classified according to these things, not because of the half-life, but because of the volatility. This is perhaps the most important thing. Of course, amount in the nuclear fuel too. All right, let's look at the radionuclides from nuclear detonations. And nuclide distribution, it depends on the type of the bomb. Fission or fusion bomb. There are, of course, other types of bombs too. And also structural materials of the bomb. These materials are activated by neutron activation. As said here, you have to remind that ground materials, soils, can be activated too in case of low altitude detonation. I think that you already know that, for example, atmospheric nuclear tests, they are forbidden. I'm not sure about this word forbidden, but most countries obey this rule. However, there are some countries, for example, North Korea. Fortunately, they haven't exploded this in the atmosphere. They have done underground tests. Also, France has done in Mururoa area some nuclear tests. Fortunately, in this case, noble gases are the only relevant radionuclides, and they are not generally very dangerous in terms of doses to humans. Because if you inhale them, they don't stay in your body, they will go out in the same way. All right. In the previous, I said in the previous slide that there is a Nordic project known as TEMEDET project. They made calculations on radionuclide inventories in the case of nuclear explosion, and this is the list of their calculations. They calculated a list of radionuclides according to the time from the detonation, 30 days, 100 days. And as far as I understand, they are in the order of activities. Higher activities are here in the top of the list, lower activities in the bottom of the list. And again, large number of data can be found from the net. All right. Do you know CTBT agreement? So most countries obey this agreement, which denies to do atmospheric nuclear test. There is a separate organization in Vienna that make monitoring of radionuclides, not only by detecting radionuclides, but they are using also monitors that are used in earthquakes, infrared sounds, but they are also using noble gas monitors. All right, you can see the list of nuclides. These are fission products. These are activation products, and they are following these things, these nuclides. Do you have any idea what is missing here? You can see here, at the bottom of the list, there is something missing. Actinides, plutonium, etc. And this is political issue, I think so. Because as you know that you can characterize nuclear fuel or nuclear materials on the basis of course, by analyzing these, but you can calculate different things by analyzing plutonium isotopes, for example. But this is the list of the nuclides that they did monitor, but not transuranium elements. It's a political thing only, nothing else. All right. Then there are radionuclides from other sources too. For example, isotopes used in diagnostics and treatments. How many of you are using or participating in accelerator-related things? All right. But these nuclides are produced very often by using cyclotrons. This is a specific nuclide used in hospitals. Do you have here smoke detectors? You have. In Finland, we don't anymore sell smoke detectors containing americium. This is in fact a ionization chamber inside there. But there are a lot of other products like clocks, which are radioactive, containing radium-226, for example. Watches, glass, jewels, light bulbs, camera lenses, etc. In the industry, they are using these nuclides, for example, monitoring surface levels of big tanks by using cobalt-60. Militaries, at least Yankees, they are using depleted uranium munitions. But then it is possible that some terrorists use malicious radionuclides in nuclear terrorism, I mean. Possible nuclides are these, and mainly based on source availability. All right, I think that this was the last slide. Do you have any question of this area? This is like an introductory material, so it's not very relevant on this course, but it's a background material.
Is it strontium 90?
Please use your voice so that they can hear.
I looked at the list of radionuclides in CTBT.
CTBT, yeah.
But strontium 90 was not included. So is there any
Strontium 90?
Yeah.
Yeah, indeed. But CTBT analysis or laboratories analysis gamma ray emitting radionuclides. This is the analysis techniques that is allowed in
gamma ray?
Yeah, gamma rays. Any other questions or comments?